Today we have to finish up the camera transform. And let me do a little short review of what we did last time, because it takes a couple times to see this that for you to get it. Okay, the camera transforms probably the most complex of all the matrices that we have. It's really not that complex when you finish looking at it, but there's various parameters for a camera we have to specify and everything else in order to make this thing work. Flying this camera around is one of the things you do in computer graphics. One of the hard things to do, because actually if you're thinking about doing animation and moving the camera around, cameras move kind of in interesting ways, and you can't just step it. It'll look it'll look funny if you don't move it correctly. So we'll be discussing later this quarter as we go along how to move cameras, how to do all this stuff. But right now what we want to do is get this camera transformed down. So a camera has various parameters, and what we do is we use this pinhole camera model, right, where we've got this stuff coming in to film on the back of our little camera. Okay, we use this pinhole camera model throughout computer graphics, and there's been a few people that have tried to use lens camera models. They're very, very difficult to do because they warp light as it comes in. Lens camera models actually warp the light as they come in. They're very difficult to do. So we typically stick with a pinhole camera. Notice there's no focus in a pinhole camera. Your image is always in focus, perfectly in focus. And you can get a pinhole camera attachment actually for your 35mm digital SLR if you like, which has a little tiny hole in the front, right, that you can use. But this is the model we use. So there's we use these things. We use a camera point, direction vector, or something called the center of attention. We use an up direction. We use a angle of view. A near and far distances. Okay, when we do this, these things here, these first three, are used to do orient the help us orient the camera correctly. These guys here are used to get the camera transform, get the perspective transform correct. Okay, so this one, if we look at this one, you can develop something. Let's see, I have to do it this way. If we have a camera point here, say P, and we have a viewing direction and an up vector, okay, a viewing direction and an up vector, we can typically take this. Let's see. Now the difference between most of us don't use the viewing direction as much. It's kind of a trivial thing. We use the center of attention. We kind of give a point in our scene out here, right, which is the center of attention. Right, and then the viewing direction is easy to calculate. It's just this point minus this point, right? And then we get a vector that points in that direction. Okay, and that, if you want to make it a unit vector or something, that gives us our viewing direction. So the difference, most people use something called the center of attention. it's easier to think about than trying to specify a vector. And all you do is then just subtract these two to get the vector. So some of the routines you'll see have a center of attention in them. But what we do is we manipulate this guy down, right, till it faces out on the negative z-axis. Now, first thing first is you're not going to have to do all this when you code, but if I have an up direction, the up direction may not be exactly this perpendicular to my viewing direction, right? But you can always calculate it so that it does. If you have this up direction here, viewing direction here, you can take the cross product of these two vectors to get another vector out here that's perpendicular to both. Okay? And then you can take the cross product of these two vectors to get another vector here that happens to be perpendicular to all three. Okay, and you get your little frame that way. The up direction is something that's advisory. It doesn't have to be exact, right? The exact vector, because we calculate this little frame ourselves. But so there's a matrix. What we do is we develop a matrix C, which rotates the camera, which translates camera point to the origin, and rotates so that two things happen. One, the viewing vector or the direction vector is coincident with the negative z-axis. And the up vector is coincident with the y-axis. Okay? Once we do that, and we can do this in exactly the same type of matrices we did to rotate around any vector, where we move the camera point to the origin, and then we rotate these vectors so they end up, right? We ended up along the positive z-axis. You could do it the other way. You end up along the negative z-axis, and then you rotate it finally around the z-axis so that up vector coincides with the y. Okay? Same matrix, almost exactly the same matrix. So this gives you a matrix C, and then you use near, far, and angle of view. Near, far, and angle of view to get you this viewing matrix called V, where V is equal to, we did it last time, cotangent of alpha over 2, cotangent alpha over 2, f plus n over f minus n, 2fn over f minus n, and a minus 1 right there. Zeros everywhere else, like this. Okay? And this vector effectively gives us the perspective. What it does is, if we take something we call the camera, oh, okay, I'll do this last step. The camera transform the product of these two matrices, C followed by V. By the way, some of you have discovered that already that C followed by V is different than V followed by C. You cannot multiply matrices in any order that you want. You have to multiply them in a very specific order. Okay, or you frequently don't get the things that you want. And what happens in that case, basically what happens is that your screen ends up being blank. Okay, this happens a lot. Screen ends up being blank in graphics. What happens is, quite frequently, you multiplied your matrices in the wrong order, and things have gone in different directions than where you expected them to go. Okay, but you call this camera transform here, and then you take XYZ1, any point of your scene, XYZ1, you multiply by that camera transform, and you get something out, X prime, Y prime, Z prime, and W. Okay, you get something out like this after this camera transform's done. Okay. And it's not too hard to see the C matrix will have 0, 0, 0, 1 in the fourth column. Okay? So that doesn't change this 1 at all. The only place the 1 is changed is in this matrix, and when you get done, that 1 is going to pick up the Z component that gets done after the camera transform, which is the depth of something away from you. Okay? Remember, things are out on the negative Z axis, so this has to be a -1. Remember that from last time? It picks up this depth so that this component here, the W, looks a lot like the depth of this point away from the camera position. Okay, how far that point is away from the camera position. And the idea is that the closer things are to you, they should look bigger. Farther away, they should look smaller. So the closer things are to you, that depth will be small. And when I divide by this depth here, I'm going to divide by a small thing. I'm going to make this stuff bigger. Okay, if this thing is large, and I divide by it, it's going to make it smaller, effectively. Okay, so you get back to 3D here by getting the point X prime over W, Y prime over W, and Z prime over W. Okay, and this is the camera transform. We do it all the time. Every single program, we set up a camera transform, okay, in this way. And these are exactly the operations that actually get done. What happens is that every single point that comes out of our system, right, all the polygon points, all the Chaikin's points, everything, endpoints of lines, get hit by this matrix. Okay, every single one gets hit by this matrix. Okay, every single one gets divided by W. Okay, and so when we're done, everything gets shifted in front of us. Right, so that after we divide by W, we have a point in three-dimensional space in what we call image space. Okay, and in image space, the points X, Y, Z in image space get mapped to the points X, Y on the screen in what we call screen space. Okay? In other words, we just forget about the Z coordinate. And if you remember, image space looks like this. Image space looks like this. It's a cube, -1 to 1, -1 to 1. It's a cube in image space. And when we just forget about, we take a point in image space here, and if we just forget about the Z coordinate, or effectively make the Z coordinate 0, what we're doing was we're projecting it onto that plane directly. And so we tend to think of this thing here as being our screen. Okay, or the window on our screen that we're going to plot to. So this kind of looks complex, right? It takes XYZ1, all right, for any point in space, hits it with this camera transform, moves it back, makes it into XYZW, divides by W to get the perspective, right? And then we slam it down on the XY plane, right, when we're done. If you remember, that was Y and that was Z. X comes out at you. We slam it down on the XY plane and we're done. Okay? And we've got points that we can plot. Well, there's two problems with this, right? One is that once you one is that those points, this matrix here is non-discriminant about where the points are. It doesn't care where x, y, and z are. Okay, it happily multiplies them all in. And unfortunately, those points behind us, okay, those points behind us will come out with w's. Well, let's see, those points behind us, if our camera's down at the xy, at the origin, looking out the negative z-axis, those points behind us have positive z values, right? When we get there. Those things with positive z values end up with negative w values, okay? And when we divide by a negative number, what happens is all those things get flipped over upside down and backwards in front of us. Okay, makes your pictures look kind of interesting. Okay, when the things outside the view get flipped over upside down and backwards in front of you, it makes it look kind of interesting. You know, so we have to take those things out. Okay, the other things we have to take out are those things that are outside the pyramid. Okay, we don't see those. Okay, and typically they will be out, but it's easy to take them out, and I'll show you how. So that's one thing we got to fix. Right? We got to figure out how to take those things away, and that process in graphics is called clipping. Okay, it was a process that kind of got finalized, started to get finalized in the late 70s after many gyrations, and in the early 80s it kind of did get finalized. And then the other thing is to figure out, well, if we're only plotting 2D stuff over here, if we're only plotting 2D stuff, how do we tell whether something's in front of something else? Okay, because if we have something in front of something else, we want to obscure, if it's opaque, we want to obscure the things that are behind it in order to make the image look realistic. So we have to do those two things, and actually those two things are kind of easy to do. So let me start on these. It'll take me probably 2 lectures to finish them up. But now there's something that's always called the viewing pipeline. This was coined by some people in 1982 when they built the first graphics engine. The daunting thing about computer graphics in the late 1970s was that every single point had to be multiplied by this matrix, right? Which took, in those days, forever. Okay, so if you had something with 1,000 polygons, it took a long time to generate a single picture, okay, or whatever. Now we do things with millions of polygons pretty routinely, okay. But we have to realize every single point that we have, no matter what it defines, has to be hit by this camera transform. Every single one. And so typically we have something called the viewing pipeline, where the first thing that happens is the point is hit by the camera transform. I'll show you why we separate these things in a minute. We actually do separate them. First thing it's done is hit by the camera transform. Then it's hit by the viewing transform. Okay? Then a clipping thing has taken place to make sure the points aren't behind us. Right? Then we do a divide by W step. Then, and this whole thing has always been implemented in hardware as a pipeline, and quite frequently in parallel. We can do all the matrix multiplies in parallel, for example. Quite frequently this is in parallel. And we've all learned, those of us in graphics, how to program these parallel engines over and over again. And now there's finally languages coming out. The first one you may have heard of is CUDA for the NVIDIA boards, but now OpenCL is coming out. And OpenCL will supposedly, it has to work, because there's too many people behind it, but OpenCL will allow you to program these graphics boards, not only the graphics boards, using the graphics boards, and not only programming them in parallel. We have a large-scale parallel engine on every PC that we have, but not only allow them to do them in parallel, but also allow you to program the general cores in parallel also. So it will actually be a variant of C that actually allows you to do things in parallel. Okay, and one of our former graduates here at UC Davis is one of the people that's really working on this it's joint Intel AMD type thing right now, with NVIDIA kind of sitting over on the side and watching things going on. Okay, But so we have this pipeline, and people will call it, you'll see it in the books and literature, called the viewing pipeline. Some people call it the geometry pipeline. But basically, it's a set of matrix multiply operations followed by a clipping step, in fact, followed by 6 clipping steps, okay, followed by a divide by W. The 6 clipping steps have to do with the 6 planes that bound that cube over there, image space. Okay, there's 6 of them. And those clipping steps are all done. But we can do it in a pipeline. So basically, you feed one into the top, and once that top item is done with your thing, you can feed another one in, right? And we can feed things in actually quite rapidly to these engines. So, okay, so now I've got to do clipping. And this is actually something that actually people struggled with for about 10 or 15 years before they finally got it so that it works nicely. And when you write it down, you kind of wonder, what were they struggling at? It's actually pretty easy, okay? And if you see these things over here, let's see, I need a picture somewhere of this guy that I can refer to. Here's our camera sticking out the negative z-axis with near and far, right? And what we're going to do is we're going to take this truncated pyramid and move that into image space, okay? I'm going to need this one for a bit. So the truncated pyramid is bounded by 6 planes, okay? Is bounded by 6 planes. And what I'm going to do is I'm going to do a clipping step here that shows you whether a point is inside a plane or outside a plane. Okay? Then we're going to do this several times, and I'll show you kind of how it goes. Okay? So here's a clipping step. Here's a plane. Again, 3D picture, this is a plane coming out at you. Okay? Every plane, it has a normal vector and has some point on the plane. Okay? I'll put the point over here. Some point P. Okay? Every plane has a normal vector. And this kind of makes sense, right? That if you select a point and you put a plane through think about any plane through that point, right? That we can specify exactly what the plane is by saying what the normal vector to the plane is. Okay? The other way is if you take a normal vector by itself and you think of all the planes that could possibly be perpendicular to that normal vector, well, if you select one point, right, that'll specify what the plane is. It's not too hard to see if you think about it this way. By the way, this is the way a little bit different than you learn it in calculus, at least at UC Davis. Okay? But if you think about another point Q on the plane here, okay, any other point Q on the plane, you can kind of see that if you take a vector between P and Q, like this, that this vector is going to be perpendicular to that one, no matter what Q you select, okay? That this vector is going to be perpendicular to that one. And if 2 vectors are perpendicular, you know that n dotted with, this is a Q minus P vector, you know their dot products has to be 0, okay? If 2 vectors are perpendicular, their dot product is 0. And this characterizes the equation of a plane, right? No matter what Q you pick on the plane, this thing is going to be 0, this dot product, okay? And just as an aside, the way the mathematicians usually do it is they say this is the equation of the plane. They like to say this is the equation of a plane, and it is. Okay? It turns out that A, B, C are the components of the normal vector. Okay? And if you take Q minus P here, Q is X, Y, Z. All right? And so you get the normal times the X, Y, Z part, that's this, right, the dot product. And then you get the D is N dotted with P, right? And it all works out in the wash, okay? It's all the same thing. But we like to use this one. in graphics. It makes much more sense for us. Okay. Here's your plane again. Here's a point P, and I'll draw the normal out of P, I guess. Could be anywhere. But the normal is just perpendicular to the plane. Here's a point P. Now what happens if Q's up here? Oh, let's see, I should tell you, there's two normals that work, right? There's that one and there's that one, right? One is n, one is minus n. And this occasionally causes us problems in graphics. If we don't get n pointing in the right direction, okay, it occasionally causes us some problems. And you have to be a little careful, but just a warning. There's two n's that actually work. Okay, I'm going to speak as if we use one, but there's two that actually work. Well, if I take this now, and I take the vector between P and Q, okay. Now, if Q were in the plane, this vector would be perpendicular to n, right? It's not anymore. Okay, it's not anymore. But if I look at this angle here, call that theta, okay? And I take n dotted with P, Q minus P, which are the two things. I can say that this is, you can write this in many ways. This is equal to the length of n times the length of Q minus P times the cosine of the angle between them. Okay? And these two numbers are positive, right? The length of. Those are positive numbers, okay? So it's the cosine of theta here. And if Q is on the, I'm going to call this the in side of the plane, and this side of the plane the out side of the plane, okay? The inside of the plane is the side where the vector points. Is that fair enough? Now, if Q is on the inside of the plane, I'm okay, because what happens is theta happens to be between 0 and 90 degrees, right? Okay? It happens to be between 0 and 90 degrees, and the cosine of something between 0 and 90 degrees is, I think, positive. Okay? It's positive. And so if, I can say if n dotted with Q minus P is greater than 0, then Q is in. Okay? Now what happens if Q is on the other side of the plane? Can you see I'm going to get theta, right? Again, three-dimensional picture. This is a plane, right? Can you see that I'm going to get theta is bigger than 90 degrees? And cosine of theta then has to be negative, I think. And so I can say if n Q minus P is less than 0, then Q is out. Okay, then Q is out. And of course, if n dotted with Q minus P is equal to 0, then Q is on the plane. Okay? So the test is actually pretty easy. All I have to do is take a dot product. Okay? All I have to do is take a dot product. Alrighty. Follow me? Okay.
Just to be clear, which one do we want? Do we want the points that are inside or outside?
Typically, we're going to want the points inside. I'm going to have you write a program where you're going to want both inside and outside. I'm going to have you do something, clip it, and then separate the two pieces. So you're going to need both the inside and the outside. I'll show you how to do that, though. Okay? So this is pretty straightforward, right? Just a simple dot product. Okay? Now let's have a little more fun here. Here's P, there's N, here's your plane, and here's Q1 and Q2. Like that. Okay? And now I want a little bit more info here. I want to know not only if Q1 and Q2 are in, but I now want to know which portion of the line is in. Okay? And it turns out that that's not too hard to do. Right? Now with my picture here, Q1 is positive and Q2 is negative. No, the dot product for Q1 is positive. The dot product for Q2 is negative. Okay? So I can determine this, but if I look at this point I here, let's calculate that point right there, where it intersects the plane. That one I can calculate, believe it or not too hard, because I can write I as Q1 plus T times Q2 minus Q1. Because I know that any point on the line here, right, can be written as Q1 plus T times Q2 minus Q1. I know any point on the line can be written in this way, where T is between 0 and 1. Okay? T is between 0 and 1. Let me say, let's let D1 be equal to this dot product. Oops. And let's let D2 be equal to this dot product so that I don't have to write too much. I may have to write it anyway, I don't know. Okay, and I can calculate T, it turns out. Okay? I think I have to do a couple things first. I'm going to use the mathematician's tricks. I'm going to subtract P from both sides. Will you let me do that? All right. I've subtracted P from both sides. And over here, I've subtracted P from both these guys, but effectively they cancel out, right? There's a minus sign in there. They're gone. Okay. So now I'm going to dot both sides with N. And Q dotted with Q1 minus P plus T times N dotted with Q2 minus P minus N dotted with Q1 minus P. Now I can do this, I can split this all out because the dot product of a sum of two vectors is the same as the sum of the dot products. Okay, split it all out. Okay, so this guy is D1, okay, plus T times D2 minus D1, okay, and this guy is, thank you, why? I's on the plane, right? That guy's 0. So I's on the plane. So you get out of this that T is equal to, I think it's D1 over D1 minus D2. I throw minus signs around correctly. Okay? So I can figure out T, which is actually kind of cool. Okay? Just from these dot products that I took to find out whether Q1 and Q2 are in or out, just from those dot products, I can figure out T. And if you stop for a second, usually when I do these calculations, I stop for a second, see if they make sense. Okay? If Q1 happened to be on the plane, right, then D1 would be 0, right? Right? And so you would get 0 here for T, and if you got T equals 0, you get Q1, right, which makes sense, okay? Q1 would be the point. What happens if Q2 is on the plane? If Q2 is on the plane down here, then D2 is 0. You get D1 over D1, that's 1, right? Makes sense, okay? And actually, if you look at this quantity here, if D1 is positive, then D2 is negative, so the denominator is bigger than the numerator. Right, so you've got a fraction between 0 and 1. Okay, if D1 is negative, D2 is positive, right? You get a bigger negative number than the top negative number, and still you got a number between 0 and 1. So it does make sense. Okay, it does make sense. So what can I do here? I can say, right, that I can calculate T, and I can say the part from Q1 to I is in, and I can say the part from I to Q2 is out. Okay? Now all of a sudden there become 4 cases, right? Because I've got 2 points, right? They could either have both dot products could be positive, in which case both of them are in. Both dot products could be negative, in which case both of them are out. Okay? Q1 could be positive, Q2 could be negative, right? I calculate I in that case, and I say Q1 to I is in, I to Q2 is out, or Q2 could be positive, Q1 could be negative, and I do the opposite, right? So it's possible to use the dot products. Can you see now that this is what scares people? This is what took this so long to be developed, is that every single point has to have a dot product taken. Woohoo. Okay? And all of a sudden there's lots of multiplies and adds and everything else going on. And if you have millions of points in your scene, which we do, right, that this thing could potentially take a long, long time. And back in the 1970s or so when this was being developed, which, you know, in the ice ages of computer graphics, when this was being developed, they worried about, you know, doing too many multiplies. And I'll show you how they kind of cleverly solved it here. I think I can, well, maybe I can get done with it today. Okay, so here's plain. One more. I got one more thing to do. There's N and P. Okay, and here's a polygon. Q1, Q2, Q3. No, let me do it this way. That's the example I want. Q1, Q2, Q3, Q4, and Q5. Okay? Now I want to do even more than lines. I want to say this portion here is in. Right? I want the polygon that's in, and I want the polygon that's out. Okay? If I can do polygons, well, eventually you'll find out we do most things into triangles. You can do polygons, triangles or polygons. I can clip them. Okay? And this thing is surprisingly easy to do. What you do is you write a little loop that loops through the points, right? And you make yourself 2 lists. One's called the in list, and one's called the out list. Okay? And you move these points into the in or out list, right, depending whether they're in or out. Okay? And it kind of goes like this, right? Q1 is in, Q1 is out. Let me try again. Okay? Q1 is out. Okay? Q1 is going to show up with a negative dot product, right? It's going to be out. Now Q2 happens to be in, okay? So what I do is I calculate this point here, I1, okay? And I put I1 on both lists. I stick I1 on both lists because it's both in and out, okay? Now Q2 is in, Q3 is in, Q4 is in, right? Q5 is out, right? So I calculate this point, I2, okay? And I put it on both lists, right? And now Q5 is out, like this. And here, when I'm done, I have these lists of polygons, okay? I have these lists of polygons that I have I1, Q2, Q3, Q4, and I2. This one, whoops. I1, Q2, Q3, Q4, and I2. That's this one, the one that's in, right? And I have Q1, I1, I2, Q5, which is the one that's out. And it's surprisingly easy. Now, I've just kind of glossed over lots of stuff. Go ahead.
So
by consequence, if like Q2 is in the plane, you do it in both lists.
You do it in both of them, right? You do it in both of them. I mean, simple, right? It's really simple to do. Now, there's some caveats here that I didn't do. Also, the answer to your question, too, is the answer is yes, of course. You put them on both. But one of the problems we have in computer graphics is that to find that a point is on, you have to find that a dot product is 0. Okay? And if you've worked for floating point numbers at all, you'll find that finding something equal to 0 is very difficult. Doesn't happen very often. Okay? It doesn't happen very often. And so usually when you see a computer graphics person's clipping algorithm or something else, there's a variable in there called fudge or something, epsilon, whatever. And instead of finding something as equal to 0, you find that the absolute value is less than epsilon. Okay? If it's less than a very, very small number, you consider it 0. All right? And go from there. So that's one thing. The other thing is that this algorithm only works for convex polygons. All right? Now, there's two things you need to know about graphics. Number one, polygons are planar. Right? They have to lie in a plane. You're going to find, if your polygons don't lie in a plane, you're going to find some real interesting things happening. Okay? We assume they lie in a plane. If they don't lie in a plane, quite frequently we split them up into triangles, and triangles are always planar. Right? They contain 3 points. They're always planar. Considered. We always consider polygons lie in a plane. And then a convex polygon has the property that if you take any 2 points on the boundary, any 2, okay, and you take the line joining those 2, that line has to lie completely inside the figure. Okay? So if you have something like this one is non-convex, right? Because if you take 2 points, 2 points on the boundary, try again, there, and you draw a line, that line does not lie completely inside. It's not a convex figure. Okay? Now what people do with convex figures, I'm almost done here, is the following, and this is one of the first algorithms that we got to work on, actually when I got into graphics. What we do with convex figures, non-convex figures, we break them up into convex pieces. Okay? We break them up into convex pieces. We somehow determined that there's a line through here, right, which causes a problem, or a line through here that causes a problem, and we use this line to define a plane, and we clip them. We clip these things into convex pieces. And it can be done in a nice, simple little recursive algorithm, which exists in almost every device today that's out there. Okay? So this is clipping. Okay? The difficulty with clipping in the 70s was this dot product. Took forever when you pile them all up for everything. Okay? Because what you have to do is you have to clip. If you think, let's see. If you think of our planes here, okay, I have to clip on at least 4 of these. All right? So what I'm going to do is I'm going to get 4 planes. This one. Here's my normal vectors to those planes. Okay? There's 4 planes here coming out of my little box. Right? And I'm going to clip on each one. Fortunately, a point on every plane is right there. Okay? So I can use the origin as the point P over here. And all I have to do is specify 4 different normals to get these 4 planes. So I have to do this clipping operation 4 different times, right, around these planes. Now, a really nice side effect of doing this clipping 4 different times is the fact that if there's a point out here behind me, it's going to be out on at least one of those planes. Because, I mean, it's going to be out, for example, on this one. No matter, if you're behind you, no matter what happens, that point's going to be out. It's going to be clipped away if you clip on these 4 planes. Okay? And so we typically do clipping a lot. You can clip on the 4 planes. We typically also clip on near and far. Okay? Clip away things that are close, clip away things that are too far away. Normally, near and far clipping is turned on. And this clipping operation kind of just goes automatically. It's part of the pipeline. I said, now, one of the things we typically do is, and I'll do this real quick next time, is we actually don't clip here, right? We clip in image space, it turns out. Because clipping is so easy if you think about it in image space. Okay? What's the normal vector to one of those planes look like? Like 001, right? Like 001 looks like the normal vector. Okay? And so this normal vector in one of these equations here looks like 001. So if you take dot product of 001 times this, you don't have to do any multiplications. You just pick out the z coordinate of this. That tells you the sign of the dot product. Right? 0 times x, 0 times y, 1 times z. You don't even have to do a dot product. And so people usually delay the dividing of by w to do this clipping process. Unfortunately, you got this really nice fact that anybody out here is automatically out, goes away. That doesn't happen anymore, and you got to do this one extra clip. So you have to do 7 clips right in this. But I'll show you that next time. Now, your assignment today is to look up Google or wherever you do 2 things: GLU lookup, GLU look at, right? And GLU perspective. Look these 2 guys up, okay? You're going to be real familiar with them by the end of this quarter. And they're going to look remarkably familiar, okay? The parameters for these things are going to look remarkably familiar, like near, far, etc.
T is capitalized.
Pardon?
T is capitalized.
No, the T is not capitalized, actually. Okay? The T is not capitalized. You can put it into Google and it doesn't care. But these things will look remarkably familiar to you, the parameters and everything else, after sitting through Ken's lectures here for a couple days. You're going to be using these things a lot. Okay, look at, use as a center of attention. Typically puts a center of attention point, which is quite frequently somewhere in the middle of your scene or something like this. Okay, and it's really easy to do. So that's the homework for Friday, is to look those guys up. Okay, look at the parameters, see what they do. You're going to have them in almost every program you do. Fortunately, all this matrix multiplication, clipping, everything is done for you in the graphics engine. Okay, it's done for you in the graphics engine. You're going to have to understand it anyway, because I'll give you a problem that makes you do it anyway. But we'll see. So I will see you on Friday.